So I'm going to talk about dynamics of consumer demand with aggregate data, focus on aggregate data. So estimating demand is really central in industrial organization and comes up frequently to me in every field of economics. Whether you, and broadly, I'm thinking about demand, whether you think of like political economy modeling, how people choose between candidates, or labor, how people choose between different professions. It's all demand estimation to me because that's kind of the framework which I view the world. And often the problem is going to be dynamic. And I'll have another slide where we kind of go through these points, but very frequently it's going to be dynamic. Most demand estimation is static. They're using static model, and I would say most dynamic models are designed with disaggregate data in mind. And so we're going to put those together here today. We're going to think about demand with aggregate data in a dynamic model. And so and then combining that brings up several issues. I just want to, kind of get definitions first. So what do I mean by disaggregate data? Disaggregate data, I usually mean household data. So we can see the household. We have panel data usually, or survey data, and we can see people over time making choices. Whereas aggregate data, don't think about just like time series data like GDP. By aggregate data, I mean, usually we'll observe sales by product. We'll see for a bunch of products how much sales they got, and we'll know product characteristics and prices and things like that. But the key thing is with disaggregate data, we can match the households to the product they purchased. We can see which health, we can see if big households like big cars, right? With disaggregate data. With aggregate data, we can see how many cars were sold, but we can't see who bought them. We're just going to have market shares, and that's going to change the way we do our estimation, and it's going to change what we can infer or how we can infer from the data. So maybe on a school of dynamics, you don't really need motivation to study dynamics, but I'll just say briefly, kind of dynamics comes up all the time in industrial organization of these different kind of classes of products, durable goods, cars, consumer electronics, appliances. You buy the product today, you're not going to need the same product tomorrow. You've got one from yesterday, and you probably your demand is going to go down as a result of having purchased the product. Storable goods. So we think of like especially consumer packaged goods at the supermarket. When they go on sale, people load up and then they don't need to buy the product. Their demand is going to be reduced for a while because they have a big store of the product. And so, this is kind of classic paper, stunning laundry detergent. But you can think of that coming up with all kinds of different contexts. Subscription services. This is kind of a broad name I'm using for any time, you sign up for something, it has some switching costs to it. Bank accounts, insurance plans, all kinds of memberships. You're signed up for a streaming service or something like that, your gym membership or whatever. There's usually some kind of switching costs involved, and that's going to induce consumer dynamics. And then the fourth one I'll just throw in here, performance goods. Once you've been to let's say there's a show in town, Taylor Swift comes to town and she's doing 3 shows, and you went to the first one, probably your demand for the second one is pretty low at that point. Probably only see it once. Or you think of, the Broadway show runs for 6 months, probably most people go only once. And so that there's a form of dynamics that's involved there. And then I have this paper on movies in China, which you might be interested in, which is about, we try to use dynamics to think about why demand drops off so quickly, from week to week from these movies. People in the first period see the movie, they don't want to go see it again. And so demand is going to kind of endogenously decrease. So we'll talk a little bit about kind of disaggregate data versus aggregate data. How do you make the choice whether you want to use disaggregate models or use disaggregate data versus aggregate data? So, oops, sorry. Not sure where the back button is. Yeah. Okay, so disaggregate data is kind of better. I mean, you get to see the household match up with the product characteristic, and that's very powerful for trying to understand demand and estimate appropriate elasticities. You can track households over time. You can see when they switch products or upgrade their product or switch their bank account or something like that with disaggregate data. And you might think if you're studying dynamics, that might be pretty important to see at least some data about that. you can often see their outside option. Like if you see them buy the car, maybe your survey data tells you what their used car is. So you know exactly what their kind of outside option is. Often in disaggregate data, we can see the transaction price. Like if someone is negotiating for a car or using a coupon at the supermarket, we'll be able to see that in the disaggregate data. And then I'll just say, you know, price endogeneity is always going to be an issue in what we're doing. And with disaggregate data, you've got many households per product. Maybe you can use product fixed effects and address endogeneity in that way. That might wipe out some of the variation you're interested in if you're interested in product characteristics to study. But at least that's kind of an attractive way forward to deal with endogeneity. So why ever use aggregate data with all these advantages? Well, sometimes it's all we have. So it's easier to get like quantity data than it is to get a good survey of household data. I'll say that it's often necessary to study the supply side. And that's because typically when we want to think about the supply side, we need to know the market shares of all the products. We want to think of this multi-product firm with all these prices. We need to know how they set their prices in response to all of the market shares. And survey data is often not sufficient for that. So you think of like in cars, sometimes people use the consumer expenditure survey in the United States, surveys like 10,000 people, but only about 10% of people buy a new car in a year, and there's hundreds of cars out there. And so you don't really get a good measure of market shares for lots of the cars from typical survey data. So if we need market shares, which you typically do to solve things about a first order condition, often we're going to need aggregate data to do that. So like very loosely, I would say like papers that kind of only use aggregate data often are maybe like you almost associate them with like marketing papers almost. They may end up more naturally in like a marketing department, where papers that come out of econ departments often are kind of using supply side, and they're often using aggregate data. And there's many violations of that. Many papers only doing demand with disaggregate data in econ departments and vice versa. But it just kind of loosely, I think that's a way to think about this distinction. Yeah. Yeah, it's just to state again. So disaggregate data is going to be household level data. I can track the household over time, see the purchases they make. Where aggregate data usually is like I have only data on how many sales there were, perhaps of many models. Perhaps I may have many observations because there might be many models and I have very granular data. But the key thing is I can't match up household characteristics to the product characteristics that purchase. Can't see is it big households that bought the data. You can't see is was the purchase an upgrade or was it like a new purchase? That we'll never be able to tell from aggregate data. And sometimes like you have individual level data. Like sometimes we were just talking about like DMV kind of a car registry data. Like you can see every transaction, you know, you can see every car transaction in the, let's say the registry of a particular government or something. Seems pretty disaggregate, but you actually don't see any household characteristics in that data. So actually you end up treating it almost like aggregate data because you can't tell. You can see, you know, maybe the location of where the thing took place and you know the zip code level demographic, but you can't see was it a big household that switched from, you know, conventional vehicle to an electric vehicle. And so you end up treating it like aggregate data, even though you really, obviously you're seeing very granular data. Yeah. Okay, so we're going to focus on this aggregate data issue because that's the data we have, but I think it's useful to kind of keep in mind, you know, how we make these choices in our research projects between aggregate and disaggregate data and what the benefits are. One last thing. Often these models are often nonlinear, and so it's hard to use kind of two-stage least squares or typical instrumental variables models. Whereas here we can often kind of extract the error term in a linear way, and then we can use moments or instrumental variables to think about price endogeneity, which can be a real advantage in some contexts. Okay, so in order to talk about how we combine aggregate, in order to think about dynamics for aggregate data models, I want to start with talking about static models. And so I'm sure many of you have already been kind of exposed to Barry Levinson and Pecos. That's going to be our kind of leading static, our leading kind of static demand model that we're going to use here. And then our goal is to, but I'm going to actually do a few slides on how BLP works and how to use BLP, and then I'll go on to adding dynamics to it. But let's just kind of say where we're going. The kind of consumer model we have, the static demand model we have in mind is this model by Barry Levinson and Pecos, and it really focuses on kind of the unobserved heterogeneity and this, we'll see the product characteristics, and we're imagining there's preferences for those product characteristics that vary in the population, and that's going to lead to hopefully realistic substitution patterns. And then we'll going to kind of think about a Rust style, like optimal stopping problem of making a choice of when to purchase with this Barry Levinson and Pecos style demand model with unobserved heterogeneity. How should we think about this unobserved heterogeneity in a dynamic context? We're going to take the position that it should be persistent. So that is, if you love price, if you're someone who like hates price and loves a big car, you have some big preference for big cars, and you're particularly price sensitive, then next period should be the same. Your preference should stay the same over time. And I'm sure you've heard this week that building kind of persistent unobserved heterogeneity into dynamic models is an issue, right? It's going to violate conditional independence, and that's going to be an issue that we're going to have to address in how we do it. And then one last point is I want to make clear, although our focus is on aggregate data, I'm going to talk a little bit about how you can kind of combine both aggregate and disaggregate data and get kind of the best of both worlds. Because ideally, we can make use at least of whatever disaggregate data we can as we go forward. Okay, so a little background, BLP 1995. So we're going to start with some products. There's going to be J products available. The products are characterized by a kind of finite set of characteristics, X's, that we observe in the data. Okay, and so like if these were cars, we might think of like size, cost per mile, which I would always put miles per gallon here, but now we're often focused on cars that don't use gas. Safety features. They use their papers from 1995. They have a dummy for whether the car has air conditioning or not, which probably isn't very relevant anymore, but would be was at the time like a very interesting characteristic of the car. And then we'll observe two more things. We'll have we will observe price. We'll see the price of the car, and we'll usually have some unobserved characteristic XC that they call XC, which I pronounce as XC, but I hear other people pronounce it all different ways. And I don't know if we have any Greek students that can kind of lay down the law on how to pronounce it, but in LaTeX it's XI. So I hear people call it chai and psi and all things. I say XC. And so yeah, I would maybe use a pen if that's helpful. But okay, so that's going to be the product side, and then on the consumer side, we'll imagine a continuum of consumers. Okay. And they're going to have some preferences for product characteristics, a new I, and that's going to tell us kind of the match of this consumer to the product characteristics that are available. So if there's, loosely we'll say, if there's L product characteristics, there'll be L preferences, new I, and that'll be like, if you draw high new for size, you just love big cars. And if you draw high new for mileage, you really want an efficient car. And so we'll imagine these kind of news are these draws or some heterogeneity that's in the population around something, and that's going to generate kind of these substitution patterns. And the consumer picks one product, or they can pick some outside option, which I'll call J equals 0. Okay, so we're going to use a discrete choice model. I mean, you've seen a lot of that this week, I think. We'll imagine the utility to consumer I. The utility to consumer I from product J is going to be a function of the characteristics. It'll be linear. I'm using alphas. That's a little bit different. That's going to line up with what I'm going to do later in the paper. Some of the notation I use here are going to deviate from BLP and use notation that sets up better for what's coming. Okay, so you'll get something from the product characteristics. You'll pay a price, and then there's this kind of complicated looking term which tells you about the match between the product characteristics and the news. So if XJ1 is size and new I1 is big, it means you love size. You love a big car. And if new I1 is negative, you like a small car. And sigma is like a parameter we're going to estimate, which tells us how important is this interaction. If sigma is equal to 0, then it doesn't matter how much match there is between the consumer and the product. But if sigma is big, there'll be a lot of that match will be will be really important. Then here's this unobserved product characteristic XC, and then there'll be the epsilon ij, which is our kind of familiar extreme value distribution, and normalize all this stuff to 0 for the outside option, and I'll just have it be, just get it below this kind of logit draw. And then it'll be convenient to think of this mean utility here. We're going to give it a name. I'm going to call it FJ. In PLP, they call it delta J. I'm going to call it F because I'm going to call that flow utility. In our dynamic context, it's going to be flow utility. So I'm going to imagine there's some flow utility. So I'm just rewriting this equation here now with, there's your kind of mean utility that each consumer gets, plus the idiosyncratic stuff, plus this extra idiosyncratic term, epsilon. And so I think the big difference when we think about aggregate data models, you might be used to thinking about epsilon as as kind of the econometric error. Epsilon explains why people make choices you couldn't explain with your x's. That's not going to be the case in this aggregate data model, because I'm going to imagine it's a continuum of consumers drawing all these epsilons. So the epsilons are going to integrate out, and they are not going to, you can't think of like, well, people drew high epsilons, that's why the product sold a lot. That's because the epsilons are going to perfectly integrate out. Instead, the XC is going to play the role of the econometric error term. We're going to think of the XC as the error term that's going to explain why sales were particularly high or particularly low. It's going to be something about unobserved quality. Okay, so here I can think about the market share to individual I or type I, which is, it depends on their news, from product J, which is that kind of familiar logit. We get this beautiful closed form solution from the logit that I'm exploiting here, where now the share that I assigns to J is going to be a function of, the exponent of their utility, which is this Fj plus the x's, and now I've integrated out the epsilon. Remember, XC is going to be in this F term. You can remember that. Okay, and this one is from the outside option, and we get this denominator as well that I get out. I think this should have been a K. I'm sorry about that. These are Ks. This should have been a K. I'm sorry about that. And this plus sign probably should not be here. Okay, sorry about that. Okay, but this is the share that type I assigns to product J, but it's we don't get to see that. Remember, we don't know what different types buy. We can't see anything about the types of people that are in our data. So we'll have to integrate that out too. And then here, this is the share that product J gets, now integrating out over those types new I. So that is, in this share, this is the product level data that we'll get that will actually have some data about. Okay, so this thing here, there's a beautiful closed form solution to the logit epsilons to get to this equation, but there's nothing like that here. So for this, we're going to use numerical integration to handle this. So we'll think about draws of the new, like maybe from a random number generator or some kind of Halton sequence or something. We'll draw the news, and we'll use those to do the integration. I'll have a slide with that. Okay, so where does that mean utility F come from? We need to get this mean utility. Barry shows that the F is invertible from the market shares in the model. It's a one-to-one relationship between the Fs and the market shares. So higher market shares means higher mean utility. In these models, we need to find the F that generates the observed shares, but there's no analytic solution for that out there. And so we're going to use a fixed point equation. So we'll set up, this is the one that BLP used. They think of like starting with a guess of F. Then this is the market shares in the data. This is the market share from your model for a given set of parameters. I think of theta, somewhere I wrote it, theta concludes all the alphas and the sigmas. Okay. So this is the model. This is the data. If my model is generating lower market shares than my data, then I'll try, this will be positive, and I'll try a higher F. And if it's generating market shares that are too high, then this will be a negative number, and I'll try and lower F. And you can imagine solving this by successive approximations, like plugging in an F and getting out a new F and repeating. And there's some more sophisticated methods out there, but usually that successive approximation works fine. So here's the whole algorithm step by step. So we'll just go through it, and then that'll kind of set us up to go forward. So I'll start with my draws of the normal new I. And I'm going to draw it from the normal. That's kind of standard in BLP. We'll draw the news from the standard normal. You could do other stuff. And there's papers that do different stuff. If they want to, let's say, constrain the news to be positive or something, they'll do different stuff here. But we'll do some draws of the new. And we're going to hold those fixed for the whole time. And then I'm going to guess theta and then guess delta. And my ordering here matters, as you'll see. Okay, and now I can calculate this Sij, the market share that each consumer type new I assigns to each product. That's that logit form that I did not repeat here. And now I'm going to use my numerical integration by taking the average over all the draws that I've done. So I've calculated this for each of the draws new I, and then I'll just take the average to get my predicted market share for product J. Now I can plug into my fixed point equation and update my guess of F, my guess of the mean utilities. And then I'll check, did my thing converge? And if not, I will update and go back to 4. And then this creates like a fixed point algorithm, okay, like a loop that I need to solve in this estimation equation. Once I get out all the F's, I messed up and wrote delta here, I'm sorry. So anyway, this should be F here. Okay, well, now I can go get my error term, which is the XC. Remember, XC is the econometric error term. So I'm going to take F, subtract off the other stuff that determines F and get XC, and then I'll form a moment, and then I'll construct like a GMM objective function, get a new theta using, whatever optimizer you're using, and then with my new theta, go back to 3 until there's convergence. So part of the reason I put this up here is I really want to emphasize that BLP involves a nested fixed point algorithm to it. You often hear nested fixed point algorithm in the context of like a Rust dynamic model. This is not a dynamic model. We're using the fixed point algorithm to back out a nonlinear error term. Okay, the error term is kind of nonlinearly embedded into the model, and so we're using the fixed point algorithm to back it out. We're not doing dynamics here, but still we're using a fixed point algorithm to solve the problem. To me, the word nested fixed point algorithm could be just as easily applied to BLP as it could to Rust. Often when you hear people say the word nested fixed point algorithm, they mean the kind of Rust style dynamic solution, but it could be here too. That might raise a question in your mind because I'm going to use dynamics now, and like there's a fixed point algorithm coming from the dynamic side, and there's a fixed point algorithm now coming from the demand estimation side. It's going to be an issue that we'll have to kind of deal with there. Any questions about all this? This is kind of my BLP presentation. So I'll just say, kind of the takeaways. What is the point of all that? Like, what did we get out of doing that? So the random coefficients in the low utility model are going to allow for much more realistic substitution patterns. That is, this would all be easier if we set the sigmas to 0 and there are no random coefficients. That tends to generate really kind of far-fetched substitution patterns. And these sigmas are going to allow us to kind of match that much more accurately. So we'll see that people substitute. Let's say people that buy big cars substitute to other cars that are big because the reason they bought the big car in our models, they draw high new I for big. So then when you take away or raise the price of one big car, they substitute to another big car. The model is going to lead to a nested fixed point algorithm to obtain the error term in this kind of nonlinear model, and that's where the fixed point that's where some of the numerical problems with BLP come. Just kind of loosely, like what is sometimes we call it identification, or what is the variation in data that tells me about my parameters? I think the intuition I want you to have in mind are, when we see XJ go up, we see one of the X's go up, market shares, let's say, go up, that tells us that the alpha, the mean coefficients must be big. Okay, so that's kind of standard, like logit type intuition. The great thing with the random coefficient models, now we're going to make use of more variation, which is where did that market share come from? Okay, so X goes up, market share goes up, but it had to come from somewhere. And did it come from products that are nearby in product space or just diffuse across all the products? In simple logit, where the sigmas are go to 0, you take market share from all the product. But here, if we see that market share came from other big cars, we'll know that the sigma for size was big. Or if we see that market share came from, cars with air conditioning, but not cars that were different in some other way, we'll be able to kind of figure out whether the sigmas for those products are big or small. So we'll try to keep that kind of intuition in mind as we think about how the kind of how does the data, it's not a complete black box, like it's supposed, these parameters should reflect something in our data, and that's kind of intuitively how it should work. Okay, so now we're going to switch over. My application is consumer electronics. So we're going to use digital camcorders as our main product that we'll be focused on. So it's a bit of a dated product. I'm not sure how many of you own a digital camcorder, because like your phone now kind of wiped that out. But for a while, they were like a pretty popular product that people were buying. And I think everyone has the sense when they're thinking about buying consumer electronics that price is falling over time. You know, if you think of like the newest kind of cool television or whatever is the new thing coming out, price is falling over time. And if you kind of wait, you could maybe spend the same amount and get a better product. The quality is going up over time. Okay, and so to us, like, for me, as I think about this market, like dynamics are just a first order thing that every consumer is thinking about, not just what to buy, but when to buy their product. And so we thought this was a really natural place to kind of think about consumer dynamics as we go forward. Here's some data from our digital camcorder data. It's product level data. So it's just simple averages across all the products that we have. Our data set's going to go from January 2000. It's basically the beginning, like the first digital camcorders. There was a previous market for analog camcorders. They use like tapes to record this stuff. These are going to be digital. Okay, so we get right from the start. And you can see sales going up over time. That's the red line. You might notice some periodicity in this data, some seasonality. So, Christmas just like jumps off the page whenever you're looking at this kind of data. And I'll just sort of sheepishly admit, we don't have a great model for what happens during Christmas. So a big chunk of what we do, we're going to kind of de-season the data and match this kind of the green line there. But you can see also here, price is dropping, dramatically. So like starts at this average of 600 and drops, really precipitously over time. So it's just, these kind of changes over time are really for sort of features of the data. We also have data on DVD players, and same thing, no surprise. Prices are dropping, sales are growing, tons of Christmas effect. There's like a Father's Day, there's like a June Father's Day, or in the US it's Father's Day and college graduation or something else is in it. One thing that's interesting with our DVD data is you can see the drop off at the end. Like now you can see kind of the beginning of the end for DVD players. And so, as people get into other ways, kind of other ways of watching movies, like, what's that? Yeah, I'm not sure streaming was really around in 06, but there's a lot of like on-demand movies through your cable system. But yeah, things are changing. Okay, so our goal is to estimate a structural model of consumer demand in the context of dynamics, and I'll talk a little bit about present state kind of applications that we can do with this model. Skip all this literature review stuff. Okay, so we want to have persistent heterogeneous consumers, dynamic decision making, and then we can apply it to aggregate data. And I have this paper that we're kind of using here as we go forward. So like, what's kind of the thing I want you to have in mind? So our whole goal in this paper is to construct this matrix. Okay, so you can sort of think like there's types of consumers. Let's say the only random draw was on the constant term. So there's people that love digital camcorders and people that don't care that much about digital camcorders. We can organize people by how much they like digital camcorders. And we'll think if we have 5 types of people, from kind of loving the product to kind of maybe not caring as much about the product. And then, and at the beginning of time, none of them have purchased. Like in period 0, nobody's purchased. So this is a matrix of shares of people who have not purchased yet. So at the beginning, it's 1 for everybody. And then the product comes out, and then the lovers of the product, maybe 10% of them buy the product, and it's less people. And so less people are buying, and so more people haven't bought the product yet. And that's as you go down this row. And then as we go forward, there'll be more and more people kind of transitioning out of this place of the matrix. And what we want to do is kind of construct a model that generates this matrix and then use it to generate market shares that will match to our data. And I think this matrix is maybe the thing that's the most different from what already exists in sort of DLP or Rust. The other thing you keep in mind is this is the share of people that haven't bought. We can construct another matrix for like the set of people that have bought a product of quality 1 and quality 2 and quality 3. And as you leave here, you move to one of those other matrices, and we can kind of keep track of how many people are at every quality level, and we can maybe allow them to repurchase or that kind of thing. And I think this somehow, I find thinking about this matrix, basically at this point, once you have this matrix in mind, we're going to make like whatever crazy assumptions we have to make on BLP and Rust to get it so it can kind of generate a matrix like this. And I'll come back to this point, I think, if we draw that. So here's our model: discrete time, infinite horizons, continuum of heterogeneous consumers, J products. Now we have J subscripted by T because it's going to change over time. We're going to assume the products are infinitely durable. That is, when you buy a product, just lasts forever. And we're going to allow people to repurchase. And when you buy a new product, you throw out the old one. You don't. So we're not modeling like the used market. We're not modeling breakdowns. We're not modeling like you give your old digital camcorder to your brother or your kid and get some utility out of that. You can't like bequest a digital camcorder. It's very simple. You just have the digital camcorder. That's the quality you have going forward, and you can upgrade on it. And we could try to take on all those things like bequests and used markets, except if we had data. We never found any good data on that, so we never did it. But of course, just keep in mind, digital camcorders, you saw what's happening with price, and I'll show you some quality variables. Like old digital camcorders just weren't that worth all that much on a secondhand market. Okay, so here's our now the flow utility, or the utility. This is the utility you get in period T from buying a product. It's going to be kind of similar before. There's going to be observed product characteristics times alpha plus this unobserved product characteristic, pay a price, get an epsilon. And these two together are going to be the flow utility that you get ever going forward. So we're going to imagine you buy the product, and then your state variable will be this flow utility. You get this flow utility every period thereafter. And you can sort of imagine like once you've bought the product, the consumer immediately forgets whether it's a Sony or whatever the character. They don't know anything about the product. They just know how good it is. They just have this scalar value. Sorry about this. They just have this kind of scalar value f, and that's going to be their state variable going forward. They'll get this kind of flow utility forever unless they repurchase. Then they'll switch up to a new f, probably higher. Okay, and then there's an outside option as well. So now we can talk about dynamics. Here's our Bellman equation, which I'm sure you have seen Bellman equations before this week. I'm gonna get the hang of this thing. Okay, it has three sets of variables in it. There's F, the quality of the product you already hold. F0 is that quality of the product you already hold. It's equal to 0 on the first day. When you're born, everybody has zeros here. Everyone's holding nothing, and they're getting flow utility of 0 from that thing. Then there's omega. Omega is everything that's available on the market. So you could think of that as all of the X's, P's, and X's that's available on the market. In theory, it should also include any variables that you use to predict future prices or what's going to come in the future or anything like that. So in theory, it could include like consumer holdings, how many people have already bought. If that predicts pricing, that could be part of your state space at all. It's everything kind of outside of your home that you're interested in. And then there'll be some vector of logit epsilons as well. And based on that, you'll make your choice between any of the products that are available on the market. If you decide to purchase, this is this top line is the utility from buying. You're going to take product J. You'll get the flow utility, and then that'll be your flow utility going forward ever after. That'll be your state space. If you don't buy, then you get with the F0 that you already had. Okay, and go in the next period, you'll have that again to get started with. That makes sense? So this is our state space, way too big, right? So I'm sure you've been hearing about numerical problems with big state spaces. We're going to need to simplify this a lot, and that's what's coming. We're going to make some good assumptions to try to get this into a simpler place. First, let's integrate out the epsilons. Okay, so epsilons are going to satisfy conditional independence, so we can integrate them out and think in terms of EV. I'm using Russell notation. So we're going to think in terms of EV of just these two state variables. So there's two state variables that matter: the quality of the product you hold and what's available on the market. So how should we simplify this state space? Let's start by defining the inclusive value. So the inclusive value is the value of being able to buy this period on the market. So putting aside the option not to buy. If I buy on the market, then what do I get? Logit generates this kind of beautiful closed form solution that I'm going to exploit here. It's what do I get? I get the log of the sum of the exponent of the mean utilities. Okay, and here mean utility is not just the flow mean utility, but also the continuation value. So I get the flow and the continuation value from all the products. So you can see this is like a scalar variable, the value of buying on the market, the kind of utility of going on the market. It goes up in the number of products because more products means you get to draw more logit epsilons, and that's good. And it goes up in the characteristics of those products, either the value this period or the future value, whatever it is. So it's kind of a scalar variable that hopefully moves in very natural ways. It gets better when the market is better and worse if the market is worse. One kind of interesting point we can make with logit is like, there's no assumption here in saying this, is just kind of a natural extension of the assumptions we already made, is that if you knew the inclusive value in every period, you would know when to purchase. Because you don't need to know the underlying product characteristics that are there. Just knowing the inclusive value is enough to make your choice, right? So your value this period of being able to purchase, which depends on all of the state variables, we could rewrite it as just a function of just the quality of the product you hold. And instead of omega, instead of a full of omega, all you need to know is the inclusive value today and your prediction of the future inclusive values. Right? So if you knew like your inclusive value today and your prediction of all the future inclusive values, you would not need to further know omega. Now, of course, you use omega to make those predictions. So in that sense, you still need to know omega, but this gives a sense of where we want to make the simplifying assumption. Yeah, so this is kind of like I could rewrite this value function as these two choices, either to buy today, in which case I get the inclusive value that's available today, or not buying, then I get F0 and my future, this kind of future value. So where am I going to make my simplifying assumption? I'm going to make it here. How do you predict the future? The inclusive value is just a scalar, so that's very nice. I need to make an assumption about how you predict future inclusive values, and I'm going to assume that you use just the inclusive value to make that prediction. So we have this assumption, we give it a name because we thought like Rust had conditional independence and we wanted to have like a name for our assumption. Other people were using the assumption, so we wanted like a name so people would like talk about it in the same way. Not sure it really worked out, but we did give it a name. We call it inclusive value sufficiency, which is to say that you use just the inclusive value to make your prediction. So formally, this says that if two different states, omega and omega hat, generate the same inclusive value delta, then their prediction for how the future deltas will evolve is the same. Okay, and then if that's the case, then you only need to know the inclusive value today. There's no value to knowing omega as well. Okay, and that's going to imply a state space that has only two values, two scalars to it. The F naught, the value of the product you hold, which is a scalar, and whatever is available on the market. And so now our Bellman equation is getting much simpler. We can write the Bellman as a function of just the quality of the product you hold, this scalar value that captures the value of buying on the market, and you make this kind of binary choice between either buying today and getting the delta, which remember has the continuation value in it, or not buying and then getting the continuation value from that. So like what is the, I'm not sure I have the right slide on this. In practice, how are they going to make the predictions? We can kind of compute delta in every period, assume that consumers use an AR1. So we'll assume that they just apply an AR1 to this and make a prediction for they use these parameters gamma and sigma being the variance of this eta, to make all their predictions going forward. So formally, we're making a rational expectations assumption, but within this restriction of using this functional form. So let me say let me take a step back and just kind of talk about what is the content of this assumption? Like what are we kind of ruling out here when we say this? So you can imagine two market structures that lead to the same inclusive value. One would be there's one product on the market which has very low price, or there could be 10 products on the market with high prices, right? You can imagine those two leading to the same inclusive value. You know, the low price makes up for of the one product market, makes up for all the options you have in the 10 choice product. And somehow those generate the same inclusive value. Our assumption is that when consumers see those two worlds, they think future inclusive values are going to be the same. You could argue about that. You might think, hey, I'd rather be in the world with 10 products, as I think that's going to evolve better than the world with one. We're kind of ruling that out. We're assuming that if these two different cases lead to the same inclusive value, then it's going to lead to the same future going forward. I'll just say this is kind of the big assumption we made to go forward. Sometimes I present the paper and people would think it was great. They say like, yeah, people just kind of know like how good is the market and how fast is it getting better, and that's all they really know. Why get more involved in modeling more? And some people really objected about all the, you know, when you make assumptions like this in a room full of economists, they can be really creative about ways that your assumption is like ruling out important dynamics. And so, you know, we heard it all just say that this is kind of the key assumption for us going forward. One thing, you know, one problem we have is like, hey, this market is getting a lot better. You saw it over time. We're using this infinite horizons dynamic model. You know, we need something about stationarity to solve the model. Like, how can we possibly think of like a market like digital camcorders being stationary? So yeah, part of my response is like, hey, I want to study consumer electronics and things like that, not just laundry detergent. So, you know, back off. But I think the more technical response is with an AR1, we're imposing that eventually the deltas will asymptote. There's going to be like an ergodic distribution for where the inclusive values are going to end up, and you could sort of think of that as where the market ends, and I just do backward induction from then, and I never need to know time. So it's not that time matters to the consumer. They just know where's the inclusive value today, how far is it from where it's going to eventually get to, and they can do all their dynamic programming from there, and it's effectively like a stationary model in that sense. Okay, so what kind of criticism do we get now? No oligopoly model justifies the error one. We each worked on it. How can you write down an oligopoly model where that kind of rationalizes this error one? We found it very difficult to do, even with very, very strong assumptions. Okay, so what do? We're going to do some robustness checks. Okay, so we can let the consumer make predictions with more than just the inclusive value. We could run an AR1 and include more variables in the state space, like number of products. You could say no. Now they're thinking that they're making predictions about future inclusive values with both mean utility of the inclusive value and the number of products. We can we actually solve the model with perfect foresight. It's actually easier than this model that I'm showing to you now. And we do some other stuff. We have some other specification tests. We have some Monte Carlos where we generate data from like a fully blown kind of dynamic model and try to match it with our model and show how well we do. So we do a lot of stuff to try to get it to go, to kind of convince people, like my referees, which may or may not have included John Rust, who was whoever was that referee, like really wanted to see a lot. But anyway, you know, that was kind of the goal. Okay, the second kind of objection that we get is that we're making an assumption on endogenous behavior. Because remember, this inclusive value has the continuation value in it, right? The inclusive value has it's the flow utility you get today plus the continuation value. And you know, normally we kind of object to making functional form assumptions about endogenous stuff like the continuation value. Like we know consumers are optimizing themselves and that's creating the value function. And how can we assume that follows an AR1? Like that, you could imagine that objection. Okay, so here's an alternative. This is based on Hendel and Niveau. That gets around that objection. I was just kind of trying to show you like what's an assumption you could make that would get around that objection. Okay, let's assume that consumers don't track quality. They don't keep track of that F0 that they have. They don't keep track of the quality of the product they hold, but rather they include just an indicator for whether they have the good or not. Imagine that entering here okay, is no longer F naught, but just a dummy variable for whether they hold the product or not. Okay, now this inclusive value, okay, is the sum of the exponents of the flow utilities. People feel comfortable, economists usually feel comfortable making assumptions about exogenous stuff like flow utility, minus alpha, plus the continuation variable. Here's the thing we don't want to make assumptions about. But now this is constant for all the items in the inclusive value. Now this thing is the constant, and we can take it out here, right? And then think of this is the thing. We'll make assumptions about how we'll call this AR1. That's kind of what Hendel and Nouveau do. They'll say this is AR1, and this thing they're going to solve explicitly. So they get around it, but with this very restrictive assumption that consumers only keep track of whether they have the product or not the flow utility of the product. So for us, so I'll just say, here's that same equation again now. Here's the inclusive value is now a function of the products that are available on the market, just their flow utilities. And we can kind of write the continuation value here. So now we can make like a new flow utility, let's say, a new inclusive value just for the flow. And then we'll make our IVS assumption about this. Instead, we'll have an AR1 around this and not this, and then not this, and try to keep this part out. Okay, so then we can rewrite our Bellman equation where it's, I'm missing a parenthesis here, but there's the flow utility plus the continuation value. Now here, instead of just delta, we've kind of broken up. Now we have the inclusive value for flow plus this other continuation value. So I think it's, it's attractive because you're making maybe a more attractive assumption than what we do. But I would say, there's a requirement there, which is the choice of product has no dynamic effect. If we wanted in our model that when people bought a high quality product, they probably held it for longer, right? When people go buy a high quality product, some people like maybe buy low quality products and buy repeatedly. Some people buy high quality products and hold it for a long time. That heterogeneity was important to us, but you couldn't get that with their model. Right? So I just want to say that there's a trade-off between kind of maybe that what I'll call the Hendel and Nouveau approach and our approach, right? I think their assumption on the AR1 is more attractive because you're making it on flow utilities, but they're ruling out some important economics, which is that the choices today have only a restricted effect going forward dynamically. And I'll just say, like, I think usually like what you've been hearing about this week are sort of trade-offs between computational versus, you kind of like give up some economic accuracy or some economic phenomena to get a computational advantage. That's not this. There's no computational advantage of like theirs versus ours. This is really kind of like, what is the economics you want to capture? Do you want to have like a less overbearing assumption, or do you want to capture how choices today affect the future? That's kind of the choice here. Okay, so that's an alternative. We're going to go with ours, but I just want you to be aware that, kind of the criticism that we face and maybe how that debate plays out. Okay, so should have called this theta to be consistent with the rest of the thing, but here's going to be our parameters. Keep in mind, same parameters as BLP. We didn't introduce any new parameters. The only new thing is going to be a discount rate. We're just going to calibrate that. As you know, many dynamic papers don't try to estimate the discount rate. So I'm going to put that out here. The only parameters I'm estimating is alpha and sigma. I'm going to simulate heterogeneous consumers and then keep them constant over time. I'm going to take that simulation and have it constant over time. So how am I dealing with the kind of violation of conditional independence? Those draws of new violate conditional independence. They're persistent, unobserved heterogeneity. I'm using simulation, which is a really common way to address that. I'm going to simulate the different news and hold that constant over time, and then use like a method of simulated moments, similar to what we're already doing in PLP. For each set of parameters, I need to find the vector of product utilities that rationalizes the observed market shares, same as BLP. And I need to solve, and the vector of utilities is going to imply a solution to the Bellman equation for each consumer draw. So you can see I need both of those fixed point algorithms to be solved. So I'm going to solve both of them, both the fixed point algorithms, and I'm going to solve the two fixed point algorithms simultaneously. And then I'll be able to back out the mean utilities, regress the utilities on the X's and the P's, just like before, to get an error term and construct a GMM objective function. Okay, so I'm going to go through a little bit of kind of estimation stuff. This is a little bit similar to that algorithm page I did before. So we're going to guess now the flow utilities, also the inclusive values, and the we're going to start with our guesses for the inclusive values and the Bellman equations. I should have an I here. So keep in mind that because different consumers value the future differently, I'm going to solve for different. Here I have the I. I'm going to have to solve for the Bellman equation separately for each draw of consumers. So if I draw 50 types of consumers, I'm going to need to solve 50 Bellman equations for those consumers to be able to back out their market shares. You can kind of think like, so like intuitively what we're doing, another way to do it would be to track how all the product characteristics evolve over time. That generates a really enormous state space. So we're trying to convert this into utility space, which can be more normally thought of in terms of scalars. Right? So that's kind of, we're going to be tracking instead of how product characteristics evolve, rather how utility, that inclusive value evolves. But everybody views the different market differently because they have different preferences over size or price or whatever. So for each type of consumer, I need to solve a different Bellman equation now. So here's the, so I'm going to start with my guess of mean utility. I've guessed my parameters so I can construct flow utility for each consumer type. Then I can construct the inclusive value, this delta IT. So now I'll have, like, if I have 50 draws of consumers and I have 83 periods, which is what I have, monthly data, okay, then I'll have 50 sequences of these mean utilities, 80 lengths long, and I'll compute a separate AR1 for each of the 50 draws of consumers. So each consumer has so if you think, price, you hate price and price is getting better, you're going to kind of view the future better. You're going to think the future is things are growing at a faster rate than someone who doesn't care about price. And then the AR1 is these gammas. So the gammas are the AR1 coefficients. I'll use that to construct a transition matrix for discretized inclusive values, and then I can solve this the Bellman equation. So once I've solved the Bellman equation, now I have the inclusive values, the Bellman equation. Now I can construct these probabilities. So I can construct, this is the probability of buying each period. This is the share of people that buy each period. And then this is the share given you buy, which product do you buy? And this is the part where I'm filling out that matrix. If you can remember that matrix, now this is kind of the math behind it. Now I'm filling out what share of people are buying each period. And then given how many people are buying, which I didn't show this in the matrix, but what share is going to each product. And then I can use that to sum up to predict a market share for each product in each period. And then once I have this, I can now go update my F and get a new F and go back to the beginning and keep iterating until I've solved jointly the F's, the Bellman equation, and also the inclusive values are also a fixed point algorithm here. So once I've got my F's, I can back out my error term XC, form a GMM objective function, and go ahead and do parameter optimization over that. So here's like a picture that's supposed to help you think of all this. I don't know how helpful this is, but you can imagine I'm going to have this Rust equation where I'm updating the value function. Based on that, I can construct a transition matrix. Based on that, I can now get market shares and update my mean utility. And then I kind of circulate through all these steps until I get to a solution to jointly the F's and the continuation values. And I'll just say you don't have to kind of it often makes sense to maybe update only a few steps of each of these at a time. Like you don't have to kind of go to convergence for this, then get new market shares, then go to convergence for that, and keep going around. It's often efficient to kind of just take a few steps in each one at a time. So it's definitely computationally involved. I'll just say when Gautam and I wrote this, like we had just gotten tenure and we were like, okay, we have time, we can kind of do it, but we're gonna make this work. It was a fun project to work on. So I'll say Identification is not the right word, but this kind of this back to this discussion of like, what is the variation in data that's telling us about our parameters? Same as BLP, right? It's exactly the same as BLP. As let's say product characteristic improves, market share is going to go up. That tells us about mean utility coefficients, the alphas and the mean. Where do those products come from? That's going to tell us about whether the sigmas are big or not. The advantage to our model over BLP is that we can use where that market share came from across different periods. Like if somehow a lot of people buying the product this period means less people buy the product next period, or less people buy similar products next period, that's going to be useful variation in our model for how to identify these parameters, where BLP could never make use of data like across different time periods. That variation would never be useful for them. Okay, so our model allows for substitution both within and across time periods. That's the kind of identification advantage of a dynamic model. Okay, so I'm going to do some results, some kind of empirical results here. You can see how the whole thing worked out. And I'm going to talk actually a little bit more about disaggregate data. I'll come back to that point. But here's our aggregate data. This is the main data set we're using. We've got this monthly data, March 2000 to May 2006, 11 brands, 4,400 observations. So we purchased quantity and average price, and then we went out and kind of added characteristic data to the data set. You can see some of the, here's size of the camcorder that dropped tremendously over time. So that's like quality, people like smaller camcorders will carry around than bigger ones. That's like quality is getting better. Here's a pixel count. That's like the closest thing to like a pure kind of quality measure. People always want higher pixel count. That tells you what the quality of the camera. Of course, that's getting better over time. So, this is part of like why this is a dynamic problem, is that quality is getting better over time. So one issue that you might be worried about here is that I'm talking about upgrading. I'm telling you all about people upgrading. They buy their camera, they can go out and buy it again. So we're going to see some upgrading behavior in the model, but I only have aggregate data, right? And we already talked about like when you have aggregate data, you see sales of these models each period. You can't tell whether those sales went to people that are buying for the first time or they're repeat buyers. And so, a reasonable question that you can ask me is like, how can you possibly talk about upgrading? You can't tell how many people are upgrading or not upgrading from your model. So what I'm going to introduce here is survey data. So we found some survey from some company talking about, this is a penetration. And so this is how many households reporting owning a camcorder. And so our idea is that, if penetration goes, it's a little bit of a weird series. Like can't say we trusted it that much. And so there was some disagreement between us about how much to use this data. But I'll just say, because it kind of levels off, you stop seeing it grow after a period. But you can see basically, penetration is growing, but sales is higher than this. Sales is basically higher than penetration. And what that tells you is there's some repeat purchase. Like this is the share of households that report owning a camcorder. And our view is if like the share of household, we can compare the share of households reported owning a camcorder to the level of sales we see in our sales data, and we can infer something about repeat purchase from these data. Okay, so but how can I integrate that into the model? Now I'm coming back to kind of a point that's from the BLP literature. How can we make use of survey data? Right, I have the survey data. What I want to do is construct moments from our model to match to the survey data, and then just stack those moments on top of the GMM moments I was already using and have the model match all of those. And you'll see the importance of that in my results. But here's like an example. In the BLP literature, they call these micro moments. And so we're going to use a micro moment from survey data. And it turns out to be really powerful for pinning down all of this heterogeneity that we're trying to get. Now we're trying to get something about this like upgrading behavior in a dynamic model. If I was more in a static case, but I still might be able to use this to say something about match between household characteristics and product characteristics. Like I could extract a moment, let's say the expected share purchased as a function of income from my survey data, and then try to match it with my model. So here you see I've got, this is the micro moment I'm going to use is the expectation. What is the share of people that have ever purchased a product? This is different than sales. This is how many people ever purchase the product? If you bought one 3 times, you still are just getting a a 1 in this question. Okay. And I can construct that from my model and construct a micro moment this way. And then I'll just stack it. If you remember before, my moments were just this, Z prime XC. Now I'm going to stack this extra micro moment here. And I'm going to have the model, when I guess my theta, I'll go through the whole algorithm I described to get to this. And then afterwards, I'll go compute this moment from my data, from my model, compare it to the data, and construct another moment, stack it. And it's kind of like the best of both worlds. I'm getting both the product level, getting all these market shares you get from aggregate data, and I'm getting something about household behavior from the micro moment. Here I'm using like something about new purchase versus repeat purchases, other contexts you might be interested in. Is it big households buying big cars or something like that? You can imagine all kinds of micro moments that you can build in from whatever survey data is out there. And this turns out to be a really powerful way to kind of improve the quality of VLP type results. Okay, so here's my coefficient estimates. And so this is the dynamic model now without having imposed the micro moment. So I'm not using the micro moment yet. Okay, so what do I get? Well, price is negative, so that makes economists happy usually, like to see demand is downward sloping. Okay. These coefficients all point the right way. Size is a bad thing, so size comes in negative the way you might hope. All these are basically all dummies for characteristics. The one that I did poorly on is photo capable. That's the only one that should have been positive that came in negative. I'll just say I did have a digital camcorder during this time period, and it had a photo button on it. And basically, if you pushed it, it made like a loud clicking sound, like a fake clicking sound, and kind of extracted a picture from the film that was at the same level of kind of pixel count. Like you could have just after you downloaded your movie, just extracted a frame from the movie and it will be the same as what you got. I always thought it was like the most useless thing. And I'm like defensive about it because it kind of pointed the wrong way in my empirical results. But other than that, they're all kind of pointing the right way. Okay? And then so I'll just say we have 2 random coefficients here on the constant term and price. So for all of my discussion about heterogeneity, I actually only used 2 random coefficients. I'll try something more complicated on the next slide. For me personally, I'm actually curious what like Victor and Andrew and others. I think to me, if I have one random coefficient, I want it on the constant term. I always want to have a random coefficient on the constant term because that allows the products in question to be separate from the outside option, that they kind of don't view substitution. You definitely see papers out there where they have only one random coefficient, they put it on price, and for me, I kind of prefer to see the constant term first. Here, we're going to do both, and I'll experiment with some different stuff on the next slide. It looks here like there's a lot more heterogeneity around price than the constant term. That's not right, actually, because you pay the price only once, and the constant term affects you forever. And our beta is 0.99. We've got monthly data, so we set beta very high. So you can think of like the real effect of this is like 1/1 minus beta. It's like 100 times higher. So basically, we're getting that there's a lot of heterogeneity on the constant term. Some people love camcorders. Some people don't care about camcorders. And that's really dictating the results. So I'll show you in this data, I'll show you in the results, this specification generates almost no repurchase at all. Nobody repurchases because once you bought the product, you've got some high constant term. Once you got the product, you're happy. None of these other characteristics matter. You just care a lot about a camcorder. Now you've got the camcorder, you never repurchase. Okay, so now let's compare that over here. I'm going to impose the micro moment, and you could see the micro moment. That micro moment's about how we saw in the micro moment, like the set of people reporting they held a camcorder was basically constant at the end, but sales are still positive. So the only way to match that is with repeat purchase. So how should this model match repeat purchase? Like what parameters are going to change? First of all, you see all of the quality variables, basically the parameters are like tripling. Okay, so we're going to make future quality much better. So you can see pixel count is almost 3 times higher. Zoom, also about 3 times higher. All these are better. LAMP, which doesn't change over time. Products, it's not like later products are better in LAMP. that parameter doesn't change at all. So that doesn't help you match this repeat purchase. The way to get repeat purchase is A, jack up the coefficients on the characteristics that get better over time. And B, you can see what else happened here. Wait, am I saying this right? This is the dynamic model with micro moments. Yeah, jack up the heterogeneity on price. So some people don't care about price. Now there's a lot more people that just don't care about price. So now you have people that don't care about, this is on this coefficient of the mean is -3. We've got a standard normal with a standard deviation of 0.8. That actually generates a few people that love price. They think price is a good thing. We probably should have ruled that out, but obviously it's not many people because we're several standard deviations away. But now you're getting people that, really care very little about price. So if the characteristics are getting the quality is getting much better over time, and you don't care about price, that's going to generate repurchase. So I think you can see the importance of the micro moment in dictating the results, and it really is going to affect them. It's really going to cause very, kind of like important differences. And yeah, so anyway, that's what I want to say. Any questions on all that? Yeah. This is what happens when you send your paper out to too many journals. But anyway, we have lots of we have a lot of stuff here. So here's like we add number of products to the state space. So you're predicting the future, not just with the inclusive value, but also a number of products. We do the model perfect foresight. All the results are pretty similar. We do a model where there's no repeat purchase. We call that Melnikoff model. It's based on this previous paper by Melnikoff. We estimate the model so everything now has been with this kind of, we've demeaned the data. Deseasonalized the data. That, if you remember that green line, we do a version with month dummies. Okay, so we add month dummies, and that adds 12 variables to the state space because we don't want it to be like, we want people to kind of know that Christmas is coming. We don't want it to be like a surprise every day, whether it's Christmas or not Christmas. So that adds 12 variables to the state space, and also they turn out to enter kind of a nonlinear way. So you have to search over an extra 12 coefficients. This one took like 3 months to run this version, but it was shockingly the same. And we were terrified it was going to be totally different, but actually got almost the same set of results. Here's the repurchase behavior. This is the baseline model. No repurchasing, remember, because all the heterogeneity is in the constant term. Now, when we impose the micro moment, by the end, we're getting like 25% of the purchases are repurchases. So because now we have quality is getting better. Some people don't care about price. Your quality matters more. Some people don't care about price. And so we generate a lot more repurchase in the model. Oops. Please. Yeah, sure. So so I just want to be clear. We're estimating mean coefficients. That's these are kind of mean. These affect the mean utility. Then we're estimating the heterogeneity around that mean. That's these 0.087 and 0.287 here. Let's go back one just so we're on the one that we were talking about. Okay. And then all those parameters themselves have standard deviations, like standard errors that you would estimate in any kind of sample. So I think you're asking about this part, not this part, right? Okay, so I just want to be clear. Yeah, so the way to think about the standard deviation, this is true in BOP or our model, like whether we're thinking of dynamic or static, okay, is these are going to tell you that there's a lot of heterogeneity around, let's say this is like preference for price. So some people don't care about price. They ended up with a price coefficient that was pretty close to 0. Some people hate price. They ended up with a price coefficient that was super low, like way below 3.3. Okay, and that means in practice when they buy, the people that hate price are going to buy low price products, and the people that don't care price maybe buy the high price high quality products. And then you can think, as a matter of substitution, if we were to just exogenously increase the price of the high price product, who was buying it? Just people that didn't care very much about price, people that drew like a price coefficient close to zero. So what are they going to switch to? Probably other high price products. They care, everybody cares about quality. They don't care about price, so they're probably going to switch to other high price product, and it's going to generate a lot of substitution between high price products relative to other stuff, and then substitution among low price products relative to other stuff. So we're going to get people substituting to much more similar products as a result of these random coefficients. If they were equal to zero, we'd be in the world of simple logit. Then what simple logit says is if price goes up of a product, people substitute away just in proportion to market share. They all just go to if there's a high market share price, if one product has 50% of the market share, 50% of the people, when they leave this product, will go to that product, regardless of whether the product is close in X space or not. And that's the unintuitive thing about logit. And that's what we want to get away from. Yeah. You had two questions here. Well, this will get, okay, that's a good question. So there's no parameter sort of separating people's willingness to like substitute across time relative to within time. I agree with that. The model is going to have implications for that. And so let me talk about here, you kind of set me up for this slide. So one of the things, when I teach undergraduate, intermediate, micro, I talk a lot about the importance of long run and short run elasticities. But when I teach PhD empirical IO, I never talk about it because we don't have much to say about those different. We don't have. It's hard to measure. So what we thought, an advantage. So what we can do is we can talk about the difference between long run and short run elasticities in our model. So here, what we're doing here now is wow, way far away. Sorry about that. So what we're going to do now is what happens if you raise price of every product in the market. Let's say we raise price for every product in the market. And okay, so that's the you can think about in our model, you can think about different ways of implementing that. Should it be a permanent price change? Should it be a temporary price change? Should it be a temporary price change that consumers believe to be permanent? Let's focus on a temporary price change. So everybody knows it's a temporary price. Price is going to go down for one period, but everybody knows price is going to come back up, which we impose by saying they all know that the inclusive value, and they do that AR1, they predict next periods, meaning inclusive value, we just kind of raise it up to capture the fact they know price is going to get back. Okay. So price goes up by 1% for all the products. We get a decrease in sales of 2.2% this period. So that's the short run price elasticity. But then it's a little bit small to see, but now you can see sales next period are higher. This red line, they're higher than the baseline. The baseline is the short dash red line, and that top line there is now sales are higher for the next 12 months. So we can compare the change in sales over one period versus the change in sales over 12 months, and think of that as a difference between a long run and short run price elasticity. And just as you'd expect, the long run price elasticity from this temporary price change is much lower. The short run is they don't buy this period, but then more people are buying in the periods following. So we get minus 2.2 for the short run price elasticity and minus 1.6 for the long run price elasticity. So we can kind of characterize a difference between those things. And that is my best answer, I think, to your question. Okay, so the last thing I'm going to try to do with this, that we try to do in this paper, is talk about the new buyer problem, which is if you're in the price indice literature, there's been a lot of writing about the new good problem. So price indices, like the cost of living index, which is really important for determining lots of how many labor contracts are tied to the price indices, and Social Security payments are tied to these price indices. And so how do you construct the price index? You compare prices this period and next period and weight by market shares. That's kind of the Bureau of Labor Statistics computes price indices. And the new goods problem is that sometimes, the products disappear. Sometimes new products come in and old products leave, and then you don't have anything to put in this ratio. And if you just drop them, there's like selection bias, because the products that were leaving probably would have been very low priced, and the products that come in are probably pretty high priced and not dropping that fast in price. And so that creates a selection problem. So that's been kind of the focus of the literature. We wanted to focus on what we call the new goods problem has been in the focus of the literature. What we talk about is the new buyer problem, which someone had just started writing about this time at the BLS. Remember that the buyers themselves are changing. You've got something like a durable good, which the computers were a really important thing that the BLS was working on. The buyers are changing over time, and that's going to also cause problems. So we want to characterize that, and I'll show you kind of how that works. Here's the kind of typical BLS index computed for our product. And then the PACUS accounts for the new goods problem, and that means the index drops even faster because the new products coming out are better than the old products. So people, but you can see the effect isn't very big. Like the difference between the kind of classic index and the new goods index is very close. Now let's compute kind of welfare from our model. This is kind of or like how we would calculate cost of living from our model relative to what this is. You could sort of think this is like the tax. Products are getting better and they're getting cheaper. So you could sort of think this is like the tax that would be necessary to move people back to the utility that they started with. So the BLS and the PACUS one go up and just keep going up, right? Because prices are getting better, right? So prices are getting better. So their index just goes up and keeps going up. Ours kind of matches theirs for a while, but then tails off and doesn't improve as fast. Why is that? Because at the end of the data set, most people have purchased the good already, right? So they're getting, even though prices are, the other guys see like price index is dropping, so everything's getting better. Ours says price is dropping, but now as people hold the good, that's less valuable to them. Or the other way to think about it is, even among people who haven't purchased yet, the people who are buying now value the product less. It's low value people buying at the end. So the level of welfare that's being generated by this is less than what you might think. And I'll just say, there's like some theory papers showing that the BLS price index has to be a lower bound. So when I presented this at the BLS, like some people got really upset at me that I was saying like theirs is overstating things. Like some people took it really, like some people got really like, I was surprised that people have like emotional feelings about this, but like some people got really upset and they're kind of like, no, we have theory that says it has to be a lower bound. And what I would say is like, what they're calculating in our context would be a lower bound for the prices necessary to always purchase a product of the same quality, right? Like that they can always buy a product of the same quality, but they're not accounting for the fact that the people at the end value the product less. There's the set of buyers is endogenously changing, or their demand is endogenously changing. The people at the end value the product less, either because they already own it or because they're just have low preference for this product anyway. And that generates like this bigger decrease than what you might have expected from a traditional price index. Okay, so we say the BLS computes the income necessary to allow a household to buy a constant quality camcorder each period. We compute the income change necessary to hold utility constant, and those are different. And ours has more of a attenuation at the end than theirs do. And then, yeah, this is kind of just saying what I just said out loud. Okay, the shape I think is really critical more than the level in terms of like what we're really kind of getting right. But I'll just say the BLS price index continues to drop because prices do, where ours recognizes that the later buyers are low value, either because they just don't value the good that much at the end, or they already purchased it, and so that decreases endogenously their value. That's my conclusion for today. If I have 10 more minutes, I'll show you a little bit more stuff that I've been working on. But should I take questions? How do we do it? Should I? In my classes back at BU, like if I have 10 minutes, I like squeeze in more stuff. Like I never leave a minute under overturn. Please, yeah. Why don't we take questions for a minute? This thing. Oh my God, what did I do? Yeah. Yeah. Okay. I'll say one more. Yeah. Let me say it again because I think it's kind of an interesting point. Um, so I'm comparing these coefficients to those coefficients, and I'm comparing the first column to the fourth column, basically. And I kind of showed you that chart where these don't generate any repurchase. These generated basically no repurchase. You remember the green line corresponds to column one coefficients, and this is the share of repurchase over time, generates none. And kind of what's happening is there's tons of heterogeneity in the constant term. Some people love the product, some people don't care about the product, and the people that love the product buy, and then they never repurchase. There's no point. Like the products are getting better over time, but it's not enough to make them want to pay the price. So they basically never repurchase. The fourth column does generate repurchase. And the question is like, how did the model, I'm basically forcing it to generate repurchase because I'm imposing an extra moment that's going to require repurchase to match that moment. So how does the model change the parameters to generate that repurchase? That's kind of the question that I have. And so that's the wrong slide. One, double the random coefficient on price. So now there's some people that don't care that much about price. There's more people that sort of don't care about price. And two, increase the coefficients on all the quality variables, especially the ones that get better over time. So like zoom, pixel count, size. Zoom doesn't. The zooms are getting bigger over time. The pixel count is getting bigger. Size is getting bigger. And you can see all these coefficients are bigger. Like the zoom one went from 0.005 to 0.18, basically tripled. The pixel count, practically tripled. So pixel count is getting better. That's going to make people think later on these products are way better than the product I have, and I don't care about price, so I'm going to go buy again. So then you get a lot more upgrading. So I think it's very intuitive, but yeah, sort of. It's a good question. So I don't know, can everyone hear the question? He's asking about talks about the outside option, and there's going to be some share. I need to observe the share going to the outside option. I didn't talk about that, where that came from. Of course, the data I bought is only on sales of the products, not people that thought about buying the product but didn't buy it, which is what I need for this. So a typical thing in BOP is they'll use this part of the literature is a little messy. Actually, I'm really curious what some of you guys think about this, because they'll often use kind of an arbitrary thing, like let's say like number of households in the United States. They'll use like number of households in the United States, and then you're getting a huge share going to the outside option. Because like let's say cars, maybe 10% of households are buying a new car every year, so you're getting straight up the bat, you're getting 90% going to the outside option, and then obviously tiny shares going to each car. And so we do something like that too. We have as you're asking, I actually can't remember if we use households in the United States. I think we use something lower than that, but that's kind of like it's something like that we do. For a little while, kind of in early days with BOP, there was a literature of people trying to estimate how big was this market. You almost never hear about that anymore. I'm curious what you guys think. I feel like you just never hear about that. And I think in the end, it kind of doesn't matter that much. Like it affects the level of the constant term. As you move up and down the share of the outside option, it affects the level of the constant term. And also kind of the amount of substitution that goes. So in some sense, like the coefficients on the constant term, and that's partly why I said, like, I really like to have a random coefficient on the constant term. If I had to pick one, it's always this, because this is controlling how many people switch from the goods to the outside option. And that's something we don't know that much about. So you want to handle it in a very flexible way. Like, so if you made a dumb assumption, let's say about the market size, hopefully being flexible about this constant term, it's going to address that. That's probably why I said that. And for a little while, there was like a literature. I have like almost like I can't even remember any papers. I just have a vague memory of people trying to like parameterize the number of potential buyers in some way. I think it doesn't make that much difference in people kind of never found it to be that important. Like you make your assumption, you try to make the constant term flexible, and then that's how you deal with it. Do you guys agree? I'm curious if you have like great people to answer these questions. Andrew, do you agree? I can't remember those papers. Am I the only? I have like a vague memory.
Yeah.
Anyway.
But it didn't get people care about competitive side.
Yeah, I thought you don't hear if you hear less. Yeah, so there's another question in the back. Did you have another question? Yeah. Yeah, so I think what you want to think about is like the survey data. Let's say when I think about micro moments, I'm often thinking that there's going to be some survey data. Maybe I can't get every market share out of that survey data, but I can still get something interesting, particularly about the match between product characteristics and household characteristics. So I might use what is the, average income of people that bought a minivan? Okay. And then, even though I can't get every market share for every minivan out of the survey data, I could get something more general, like average income conditional on buying a minivan. And then if I try to match that moment, that'll make the BOP model much better at matching this connection between income and preferences for a minivan or something like that. By the willingness to buy a new car as a function of income, which remember in typical market share data, I can't tell whether it's high income people or low income people that bought the car. And so if I want to say something about income, I kind of need some data like that. In a dynamic context, I think the value of the micro moments becomes even more apparent because, we're going to study something like upgrading, switching your subscription or whatever. And any of those things we talked about durable goods. Do I change my durable good? Do I store up a lot of stuff? Probably you'd like to see some data about how much people actually, what they do. Do they ever switch? How often do they switch their bank account or switch their health insurance company? Or how often do they upgrade their durable good? Like, if we're going to have that in the aggregate data model, it would be nice to have some data on actual behavior. So to me, like it's always valuable to try to get some survey data on how much switching there is, how much upgrading there is, whatever is like those different contexts we talked about, how often do they go to the movies or something like that, and put that down as an extra moment. So, I think it gives a lot more credibility to the parameter for estimating these dynamic models. Yeah. That sounds good to me. But so I'm not sure what the over-identification problem is. There's always an issue that, we have more moments than parameters. We're over-identified. We can maybe run a test to check whether, all the moments are satisfied. We have like a J-test to check whether the moments are satisfied. Those tests can be hard to pass. They're a little bit of kind of an omnibus, just like, everything you did make sense? They're not really that focused on did these moments make sense versus those moments or something, but you can do like a test of over identification and check, whether you pass the J test. It's for science, it's a good thing. It can be tough on your paper though when you're not passing the test. I'll say. So yeah. That's a really tough. That's actually a really hard thing. It's something I struggle with in several papers. I'll say, I think the problem is that, so that the problem that Andrew's getting at is like, let's say we have like, whatever I said, like 4,000 observations, right? In our data set. And that's kind of typical for BOP. It's like products by time period is your data set. So you're usually going to get a couple hundred observations. Then you go get survey data, maybe it has 10,000 observations. If you kind of weight it in your GMM objective function, the survey data swamps the BOP data, but it's often less reliable. Like, I'm off, like when I get market share data, I feel like it's probably almost exactly right. You know, it's usually you're really getting sales from the company or something like that. But really accurate with the survey. I mean, who knows what they did with the survey, you know, some online survey, like who knows what they really got out of it. And so, you know, kind of the weighting the two, like you can sort of, I think, end up in a weird place where like the survey data is swamping your sort of BOP moments and you don't and you sort of don't know what to do. So I think in some cases you see people just exogenously impose like they're going to be equally weighted or some downward weight. If you think of the BOP data really, and some people think of it this way, the BOP data really comes from the choices of like all 400 million people in the United States, then the number of observations in your BOP data is much higher. I think I would say like to point to a paper, Kalman and Gortmacher have like a new their kind of BOP. So for people that are interested in BOP, you should know there's a great Python code which helps you to implement it. Many of my students have done it. Makes it much easier to like implement this whole thing. They have a paper on how to use it, a 2020 paper, and now they have in the RAND, and then they have a follow-up paper now, like 24, which is doing micro moments. And they talk about different, they have like an appendix with 3 different ways to weight the micro moment. So I guess the technical answer, I just point you to the paper. But I think that is like in general, it's like a challenging issue. And it's a little not clear, like in like Petrin or the other, or exactly what they did. I think it's not that easy to figure out. So, but I think that paper is like the right way to, I mean, I haven't heard like any criticism, man. I think that's a good place to go to think about this issue. So it's a good question. Yeah. Yeah. No, it's less than 1. It's less than 1. Yeah, it's less than 1. Yeah. So, yeah, it's a good question. Yeah, better just coming up from going over time, but you can sort of think this pen is no good, but this is kind of the inclusive value, and then we in the paper I think we show this picture, and you can kind of, I feel like the economist with like the can opener, like assume you can see this line. So um, um, we map out the AR1. We kind of show like where it asymptotes, and it basically it's going to asymptote. You could sort of think of the world as being sort of obviously stationary here, and then the consumer just does backward induction down to here, and then our data basically ends like here is kind of like this is like cap T. So it's like our consumers think the world is getting better and it getting better past the end of our data, but eventually it's going to settle down. And that's the sense in which a stationary problem. I mean, the definition of stationarity is that they don't have to condition on the time period. And our consumers don't. They just need to know the inclusive value is here. Eventually it's going to get here. They know how long it's going to take. They don't care about T in particular. They just can think about where they're at now and where it's going to end up. So there's only one AR1 coefficient for each consumer, and it's always less than 1. I've never had a case where it came. I agree. If it was greater than 1, things would explode. That would be bad. I've never actually dealt with that. I mean, we have a paper. If you gave me 10 more minutes, I'll show you like my DVD stuff. And in both papers, we never got that in all the papers, we never found that it was greater. I agree. If it was greater than 1, that would be a problem, but we never got that. So it's always asymptoting, and that's the sense in which we're in a stationary environment. That's a good question.